We're going to talk about photoelectron spectroscopy, or PES. This will give us some evidence to help show that electrons exist in orbitals from lower energy closer to the nucleus to higher and higher energies further out from the nucleus, and also that different orbitals have different energies. UPS and XPS, where UPS stands for ultraviolet photoelectron spectroscopy and XPS is X-ray photoelectron spectroscopy. UV light is energetic enough typically to eject valence electrons from the surface of active metals. X-rays have enough energy to eject electrons anywhere within an atom if they have enough energy, so core electrons can go. So in XPF, the difference here is high energy X-rays are coming in and they can actually eject electrons from anywhere in the atom. Imagine your ultraviolet light is coming in and hits a core electron. If it has enough energy, shown on the right, it can actually eject the electron and knock it out of the atom. The BE, or binding energy, is the ionization energy it takes to remove the electron. The ultraviolet light has more than that energy, and the difference between the binding energy and the ultraviolet light is the kinetic energy that the electron leaves. And it's actually the kinetic energy that's measured, and the ultraviolet light's wavelength is known, hence its energy is known. And then the difference between these two gives the binding energy or the ionization energy of each electron. Here's a diagram showing the energy of the photon coming in as E equals h nu. Those single wavelength X-rays come in and eject electrons from an atom. And those electrons zing out with a kinetic energy equal to 1/2 mv squared. And again, the ionization energy is just the difference between the energy of the photons coming in and the kinetic energy of the electrons as they're leaving. Here's a diagram of the device for measuring energy of the electrons coming out. So here's our photon source on the left with X-ray beams coming. High energy photons strike a solid surface in a vacuum. It ejects any of the electrons one by one from atoms. Those electrons then come out and go into a detector following a circular path established by an electromagnet, and the strength of that determines the speed. Then they are caught by a detector, which then determines the number of electrons at that given magnitude. Here's another view of the device, a different diagram, showing again our X-ray beams coming in, electrons taking off, going towards the detector, and then it gets analyzed. The detector then converts this into an electrical signal and then turns it into a spectrum that then has to be interpreted. Our high energy X-ray photon can come in and knock off an inner core electron like a 1s, or it could knock off a 2s or even a 2p. The more energy it takes to knock the electron, the less energy the electron has in terms of kinetic energy. So that would be done by the analyzer, and it would just do a calculation. And so our electrons that are hardest to take away are those that have the lowest kinetic energy, and those that are easiest to take away, the valence electrons, have the highest kinetic energy. So here's what a typical PES spectrum looks like. You can see the relative number of electrons on the y-axis and the ionization energy measured in megajoules per mole on the x-axis. Now notice one thing that's different here is that this scale starts with high energy on the left and goes down to low energy on the right. Also, looking at these peaks, we see 1, 2, 3, 4, 5, 6 different peaks on this. The relative height of the peaks stands for the number of electrons. And in terms of interpreting, you typically want to start on the left-hand side here with the highest energy. The hardest electrons to take away are always our inner core. And so let's just analyze this first peak first. These clearly have to be our lowest inner core electrons. This would be our 1s level electrons, and there are 2 in that. 1s2 is completely filled, so these represent it takes 349 megajoules to take a mole of these electrons away from the 1s energy orbital. So let's look at the peak right beside it. Clearly it takes less energy to take these electrons away, so we're moving out and away from the nucleus as we go to the right. And because of the peak height being the exact same, this also represents 2 electrons. So clearly these should be our 2s2 electrons. Moving further to the right, lower energy, we have a monster peak here. And in terms of relative size, if this is 2, here would be about 4, and this is 6. So this is a 6 electron peak, and it makes sense that this would be the 2p6 electrons. So these 6 electrons are all coming from the 2p energy level. Okay, let's move to the right further. And again, these breaks just mean our scale has changed. So we see this, that the scale is not even all the way down in terms of energy. So now we have a very low energy or lower energy, and again it's a 2 electron peak here, which would certainly correspond to our 3s electrons, and there are 2 of those, which makes sense. And then we've got another peak that's a big peak at 2.38 megajoules per mole. That's what these numbers at top represent. And again, this big peak, again, is exactly the same height as the 6 electron peak, so it also represents 6 electrons. And again, the next energy level out would be the 3p, so that's our 3p6. Alright, so now we've got one other little peak here, and notice this peak is about half the size of this peak. And so in terms of height, it really represents just 1 electron. And it's the easiest electron to remove, furthest from the nucleus. It's our valence electron. And moving out past, once the 3p is filled, we go to the 4s. And this is the outermost electron of potassium. And this is your first look at a PES, showing the relative height of peaks being the number of electrons, and then we think of the nucleus as being far left, and then the highest energy inner core, and easier to take as we get further from the nucleus. Alright, see if you can determine what element this is. Notice again the relative height of peaks. Think of this as your inner core. So pay attention to the relative height and then moving out and try to determine what element this is. Here's a periodic table to help you. Pause the video and think about this for a moment. Alright, hopefully you said there's 2 electrons here, that's the 1s2, 2 more here, the 2s2, then a 6 peak electron, so that's our 2p6, so that gets us as far as neon. And then we've got another 2 electrons based on the height here, so this would be the 3s2, so this should be magnesium. This accounts for the 12 electrons of magnesium. Alright, what element is this? And as you do this, it'd be good for you to identify the sublevel and the number of electrons in each peak. Pause the video, and here's a periodic table to help you as well, the same spectra, and try to determine what element it is. And don't advance the video until you've answered it. Hopefully you said this is boron, 1s2, 2s2, and then the 2p with just 1 electron in it. Alright, try to determine what element this is. And again, it'd be great if you could identify the orbitals. Here's a periodic table to help you, and pause the video and try to determine what element this is. Alright, hopefully you got that this is calcium. It counts for 20 electrons. And starting on the left is our 1s2, then our 2s2, 2p6, and then our next block at between 10 and 1, 3s2, 3p6, and then because of the height, we know we're out in the 4s, and it's only 2 electrons, so that's our 4s2 for calcium. Try to determine this element. Here's a periodic table to help you give you some reference. Again, pause the video and make sure you figure this out before advancing. Hopefully you got that this is argon. 1s2 at 309, 2s2 and 2p6 between 31 and 24. Then our lowest energy to take our 3s2, and then finally our easiest electrons to take are our valence 3p6. And again, because of height, we know that. Here's the photoelectron spectrum of scandium. Why is the peak just to the right of 1 assigned to be 3D and not 4p for this orbital? Think about the electron configuration notation for scandium, then answer that question. Pause the video to think. Well, moving across, this is the highest energy are our 1s2 electrons, then our 2s2, 2p6, 3s2, 3p6. Well, then for scandium we have 4s2, 3d1. Well, here are our easiest to take are our 4th energy level, 4s2s, and the 3ds are a little closer to the nucleus, the 3rd energy level. That's why it's to the left, higher energy to take that electron. And so in terms of removing electrons, these 4s's are easier to take than the 3ds. Alright, here's a dual spectra, and it shows both calcium and potassium superimposed on the same graph. Take a minute to look at that. Here's some questions to pose. Why does it make sense that all of calcium's peaks are where they are relative to potassium's peaks? In other words, look at the shift and try to make sure you understand and can explain why it is that it's shifted as it is. And then finally look at the last peak to the far right, and why is it that potassium has half the size in terms of its peak height? Here's a periodic table to help you as you ponder those questions. Pause the video and think it out. Alright, hopefully you said that calcium having more protons is going to have a stronger pull on electrons, so calcium, the dark blue, is going to have higher energy for every single electron that it takes. So if we just think about the 1s electrons, for example, here, calcium is to the left, and remember that's higher energy, so it takes more energy to remove, to pull away the 1s electrons from calcium, which are closer to the pull of 20 protons than it would be for potassium, which only has 19 protons. And that argument works for every single peak all the way across. And then, of course, potassium only has one valence electron, so its peak is shorter here, less intensity in terms of relative number of electrons. Even though it's further to the right, it takes less energy to take it away because it has fewer protons. And remember that because the scale is off, this is less energy to the right. Alright, here's a true and false for you, and if it's false, please state why. Calcium with a 2+ charge and argon are isoelectronic. They both have the same number of electrons at 18. So, they should have identical photoelectron spectra. True or false? Pause the video and think about that. The answer would be that no, they do not have, this is false, they do not have the same photoelectron spectra. Though they have the same number of electrons, calcium has 2 more protons, so it is going to have a stronger coulombic pull on the electrons from the nucleus, and that will mean that its spectra will be shifted to the left towards higher energy for every single electron that's removed for calcium 2+ than the same spectra for argon with only 18 electrons. Here's another true-false for you, and please, if false, state why. Isotopes of oxygen 18 and oxygen 16 should have identical photoelectron spectra. True or false? Pause video before advancing. True. Isotopes only differ in their number of neutrons. Neutrons don't affect the coulombic attraction or positive charge in the nucleus, so it will not affect the photoelectron spectra. You should be able to sketch a very simple PES with relative heights of peaks and also rough energy estimates. Again, don't worry about numbers at all. We're just looking at whether something's further to the right and therefore has lower energy or further to the left and has higher energy. So make a rough sketch as best you can for silicon and just think through its orbital notation and how far its electrons would be from the nucleus and how relative energy, and try your best on that. We'll go over an answer for that in class. I'm not going to put that in the video. Alright, try it again. Do a rough sketch for nitrogen. Pause the video. Go ahead and do this before advancing. Again, this is something we'll cover in class. We won't have the answer here in the video. An interesting website you should check out from University of Arizona. The only thing that may confuse you a little bit is they are reversing the energy here. So this is sort of the way you're used to looking at energy. Higher is to the right and lower is to the left. So once you've gotten your mind set on what we just went over, this may confuse you a little bit, but I wanted to present it just because I think it's fun and interactive. You can look at a single element as we're doing here, or the next slide will show you a dual element. So on a single element here, we've chosen scandium, and at the top, the 433, that would be the 2 electrons for the 1s2, and then 2 electrons for the 2s2 at 48, and then the 6 electrons for the 2p6. Again, this is reversed from the way we've been looking at it because the scale is now changed to lower energy to the left. So here are our valence electrons that are out here for scandium. Next inner core would be the 3p2, 3p6, and then here we are again showing the 4s2 here, and then the 3d1 for scandium. And we'll go to the next slide for a dual. And this is a way you can look at 2 elements at the same time. So I've chosen magnesium and calcium. And again, just taking a minute to look at this and explore, I think will be fun for you. And comparing numbers, for example, again, our inner core electrons for magnesium with fewer protons is 126, whereas it's a much higher value, 390, for the same taking away the 1s2 electrons for calcium with many more protons. You could look at the valence electrons. There are 2 valence electrons for magnesium. There are 2 valence electrons for calcium. They're much easier to take the valence electrons for calcium because even though it has more protons, those electrons are much further out from the pull of the nucleus, so it only takes 0.59 in terms of energy versus 0.74. So again, I think you'll find some interesting things if you spend a moment looking over that or going to that website, going back to this website and spending some time there and playing around. So that's a quick overview of photoelectron spectroscopy. Just as a quick review, incident light is coming in from X-rays and they can zap electrons out of atoms from any level. The electrons then go off to a detector and their kinetic energy is measured. The difference between the photon's incoming light and the kinetic energy of the electron allows us to calculate the binding energy or the ionization energy of every single electron within an atom. And so yes, we now know because of PES much more about evidence for the orbitals and where electrons can be and the energy in each relative orbital. And finally, we can look at complex diagrams like this and actually understand them quite clearly and even draw them for other elements. Hope that made sense to you. Review as needed. Take care. See you later.